For this concept, set your compass at an arbitrary distance and consider this distance as 1 unit. Draw 3 separate lines at a 1:2 ratio that demonstrate the following statement. A is to B as B is to C as C is to D. The arbitrary distance creates our base unit. The 2 units together create a 1:1 ratio. Using that same unit, we draw 3 sections, and it's divisible into a 1:2 ratio. 1 unit to 2 units. We can draw that in a similar fashion with a different size, a different arbitrary size. However, these two are not proportional. Although both of these are 1:2, they are not proportional to each other because they do not have a similar base dimension. That would be like comparing 1 cup of rice to 250 milliliters of rice from the analogy in video 2. If we apply characters to these units and proportions, we can then compare the proportions. Length A is increased times 2, creating a geometric sequence. A is to B in a 1:2 ratio. B is twice the size of A. B is 2 units long. C is 4 units long. Therefore, C is to B in the same times 2 ratio or geometric progression that B is to A. Line C is 4 units long. Line D is 8 units long, consistent with the times 2 proportional ratio. These 4 lines create a geometric sequence of numbers that could be used in a design with a proportion of 1:2. Therefore, line B is to line A in the same way that line C is to line B, and line D is to line C. This progression of lengths can also be demonstrated using simple geometry. This method creates the related ratios without the use of any type of mathematics or numbers. This geometric progression of lengths begins with an arbitrary single unit. This geometry creates an equilateral triangle where each side is exactly the same length, the length of our single unit. As this geometry progresses, it creates another equilateral triangle. This triangle is 2 times the size of the previous triangle. The single unit, unit A, is 1 length. Unit B is 2 lengths, a 1:2 ratio. For example, if you were designing a window where the window opening was a 1:2 ratio, You could use the width of the window as your base unit, or the length of one of the sides of the original triangle. The geometric progression would produce lengths that could be used for the window mullions, the size of the panes, and the size of the trim around the window. This method was useful in pre-industrial times for replicating a design when standardized dimensioning didn't exist. So regardless of the size of the window, the proportions of the original design would remain the same. Using this method, the original single unit could be expanded or reduced to practical sizes. This process creates a sequence of lengths related by a common length and a ratio. Geometric progression was introduced in the previous video, and these lengths could be used to design the height, width, and depth of the volume from page 313. The lengths could be measured to create numerical dimensions, or they could be directly applied from the drawing with no numerical notations. As mentioned earlier, this figure can be geometrically expanded and reduced to increase the amount of related lengths in the sequence. Each length is increased by a factor of 2. This creates a geometric sequence. This is easy to figure out mathematically. However, the geometry demonstrates a clear and concise method. The sequence of related lengths would provide the measurements for the details in a design, unifying all the elements.